we are going to begin in a minute, but so if you just run that, and if it doesn't succeed, there's a section where we're going to break to actually build, and I can come over and help you. Cool. Great. Let's move to the beginning. Okay. For the people who just came in, if you didn't do the pre-install stuff, we will get to it in a couple minutes, so it's not critical that you've done it right now. I think, yeah, starts it now, so cool. So thank you everyone for attending. My name is Joe Jevnik, and we're going to talk about C extension modules for Python. So to begin, what is an extension module in the first place? So an extension module is a module written for use in Python, which is itself not written in Python. And almost always these modules are written in C or C++, and that's because the CPython, which is the standard interpreter, has an API exposed. But it doesn't have to be written in these languages. There are projects that write them in Go or Rust. But for this, we will be writing them just in plain C. So why would you want to write one of these modules? So the two primary motivations are to interface with an external library that's written in C or has some binary interface, like something that you'd have as just a shared object, or to write numeric or performance critical code. So projects like NumPy and CyPy make heavy use of C extensions for performance reasons. I'd also like to stop real quick. If anyone has a question at any time, this is like an interactive thing, so please ask it. I don't want to lecture the whole time. Like feedback. Cool. There's also a third reason. And I think it's maybe more important than these two, and that's to understand how Python itself works. The C extension API really teaches you a lot about what happens when you execute any Python code, and it kind of peels back all the abstraction that Python presents to you. So it's a really great way to understand how the interpreter does anything at all. So even if you don't need an extension module for either of these reasons, it's great to know how they work so that you know how Python itself works. Yep. Yeah, exactly. So you could write like a wrapper module. Sorry, the question was, is a C extension a good way to expose existing C code to Python? And yeah, that falls in the first category of like interfacing with an external library. It could be an internal library or a library that's been presented to you. So I'd like to give some just like quick explanations for like when you would want to interface with an external library. The first thing you want to do is go check PyPI. Go look to see if anyone's written this before, because writing a C extension is not an easy thing, and you don't want to have to maintain your own C extension if you don't have to. So like most importantly, don't think, I know how to write a C extension, I'm going to write a C extension. Go see if it's been written first. Most popular libraries have one written already. For the writing numeric or performance critical code, again, check through NumPy, check through CyPy, look at pandas, see if the routine that you're looking for has already been written. If in that case, it's probably going to be better optimized than just like whatever you wrote quickly. So these are just, and if that doesn't work, even invest in other tools first, like at NumExpert, look at Numba. Again, I just want to throw the warnings out first. Like, remember that you don't always have to write a C extension. It's sometimes better to look to see if one has been written for you. So given that we understand all the warnings and we know we've looked and the library doesn't exist or the routine doesn't already exist and we want to write one ourselves, how do we do that? So to begin, we need to talk about how does Python present objects to us in C. So show of hands, how many people here are like very comfortable with C? Everyone? And everyone understands how pointers work or familiar with using them? Cool. If anyone doesn't know, I can explain it quickly. All right. So C is a statically typed language, so we need to know the type of everything at compile time. But Python is not. It's a dynamically typed language. We can just pass object. Turn it down. Is this better? Great. Thank you. So Python being dynamic means we don't always need to know the type of everything at runtime. So when we want to interface these, C gives us one struct called a Py object. So this struct has two fields, the ob ref count and the ob type. So I'm going to start with the ob type because it's a little easier to explain. So the ob type is a field, and it points to an object which represents the type of the object as a value. So for example, if we've got an object in C that represents a string, then the ob type is going to point to the PyUnicode type object. And that is a PyType object. So we should access this field through this macro called PyType. And I'll talk about why we need to use this macro in a bit. The other field is the ob ref count. And this is of type PySizT. And that is a type provided by the CPython API, which is equivalent to like the POSIX SSizT, which means signed size t. So it can hold any size or a negative value. This SSizT is the reference count, which is the number of people who refer to this object. So CPython uses a reference counted garbage collector. So every time you create an object, it begins with one reference, and the person who created it owns this object. If you ever want to take ownership of this object, for example, storing it in a container like a list or a dictionary or binding it to a new name, then you take ownership of this object. So you increase the ref count by 1. When you're no longer using the object, for example, you delete it from the list or delete it from the dictionary, or the name that you've bound it to goes out of scope, then the reference count will be decremented. And if at any point the reference count hits 0, that means that no one can refer to this object anymore, and it's not needed, and it will be immediately deallocated. So this is different from other types of garbage collectors. For example, in Java, an object can go out of scope and be allocated but unreachable. Objects in Python will always be deallocated as soon as the reference count hits 0. The macros that manipulate this are PyIncref and PyDecref. So PyIncref simply increments that pointer or that counter for you. PyDecref decrements it and then does the check to see if the object needs to be deallocated. So you saw that the type slot was not PyObject, but it was instead PyTypeObject. And that's because this PyObject is very abstract. We don't know anything about the data of the object. We just know its reference count, and we know what type it is. So once we know what type it is, we can have a more concrete type, which has all the data on it. So this is how you represent subclasses of object or subclasses of another type in the C API. So for example, the PyTypeObject struct has its first member as a PyObject by value. And then any instance data follows that. So this is because in the C standard, you are allowed to cast a pointer to a struct to a pointer to its first member, or vice versa. So if I have my first member as a PyObject, then I can always cast that to a PyObject pointer or cast that from a PyObject pointer. So this is kind of how we talk about a more specialized value once we've checked the type pointer and we need to actually get any data. You can check this, and the reason that we want to use those macros like PyType or PyRefCount is because it will do this casting for you. So if I have a PyType object, it will cast it to a PyObject and then access the members. So far, does anyone have any questions? Cool. So we kind of went through that quickly, and I think it's best to work through an example. So if we want to write a new function in C, the first thing we need to do is start with just a plain C function. So this is a simple Fibonacci function. How this works is not super important, or if it works. But so this function takes an unsigned long, which is an argument, which is the Fibonacci number to calculate. It returns an unsigned long. And none of these are Python values. None of this function is Python aware, per se. This only acts on C data and returns C data. So that doesn't work with Python because Python has everything represented with these PyObjects. So we need a way to convert to and from unsigned longs to PyObject pointers. As a little note, you'll see that this function is declared as static. It's always good practice to declare your helper functions as static in C. It's especially important in this when you're writing an extension module, because every extension module or the interpreter itself gets linked together into one large binary, and you don't want to have, C has one shared namespace unless you declare things as static. So static is like a private function in C. So we've got our unsigned longs, and we need to go from a PyObject pointer to an unsigned long, and we need to go from an unsigned long to a PyObject pointer. So there's a more concrete type, kind of like PyType object, for representing integers, and this is called a PyLong object. And this represents the int type in Python. I'll say now this is all in Python 3, so some of this is a little different in Python 2. Most of it's applicable, but this is one of the cases where things are different. So the reason this is called a PyLong object instead of a PyInt object, which would make more sense, is that in Python 2, int and long were different types. Integers were fixed width integers, longs were arbitrarily sized integers. Python 3 merged these together, and they called it an int, but it's all the code from the long object in Python 2, so they didn't change the C API. So when we say PyLong object, we mean Python int. So ints are primitive types in C, and Python, the CPython API gives us functions to adapt these objects to and from C types. So there's PyLong from unsigned long and PyLong as unsigned long. And this from unsigned long takes an unsigned long and returns a new PyLong object represented as a PyObject pointer. And PyLong as unsigned long goes the other way. It takes a PyObject pointer, which must point to a PyLong object, and returns the unsigned long, which is the value of that. So we can write a little helper function called pyfib, also static, but now this function acts on Python level values. So it returns a PyObject pointer, and it accepts a PyObject pointer for self and a PyObject pointer for n, where we are going to convert n using PyLong as unsigned long and get an unsigned long back. We're going to feed that to our cfib function and return the result as a PyObject pointer, and then return that. So we have a self argument, even though we don't actually need it, and that's because in the C API, every function takes a self argument. And if you're a free function, meaning you're a function that's not a method of any class, self is the module that it's associated with. And this is how you can pass around global state, because Python does not have closures. Or sorry, C does not have closures in the same way that Python does. And then n is going to be our the argument that we want to pass to fib. We're going to also ignore the fact that PyLong as unsigned long needs a long object, but we don't know that n points to a long object. So we'll cover error handling later. Yep. You don't need it. There's different type. Right now we're talking about, we're going to define an argument, a function with exactly one argument, and a little later we'll talk about functions with more complicated types of arguments. For example, like optional arguments and things like that. So we've got our C function, which talks the Python protocol per se, so it knows about PyObject pointers. But we still need to create a callable object so that we can give this function object to Python so that we can call it. Because in Python, everything is an object, including functions. So we need to define some object that represents our C function, which we'll call our cfib function. So to define this type of object, we use a structure called a PyMethodDef. So the PyMethodDef takes the name that the name as it should appear within Python, a pointer to the function which speaks the Python protocol, a bitmask of flags which tell Python how to invoke our C function. And this is kind of where you would tell it what kind of arguments you would have. And then you have a docstring. So starting with the docstring is just a const char pointer, but we define it with this macro pydoc_var. This macro simply says const char pointer fibdoc equals that string. However, you are able to compile CPython without docstrings for systems that are memory constrained, or you might just want to compile this single module without docstrings. So if you use this macro to define all your docstrings, it will respect that argument so that it won't add those docstrings to the binary. If you're not resource constrained, you can just use a string, but it doesn't hurt to use this to allow people to do that in the future. So then you'll notice that for our flags, we've selected just meth-o. And that means that our function takes exactly one object, or exactly one argument, and it should be passed to our function as a PyObject pointer. And that's corresponds to the n argument. So self is implied, because all functions need self, and then meth-o says we get one extra argument. And then we have our pointer to our function itself, cast to a PyC function, which is the function to call when we call this method object. So the method def is still not a PyObject itself, though, because you'll notice it doesn't have a type and it doesn't have a ref count. So this is just a specification for defining a method. It's still not the method itself. And the way we actually create the callable is we need to put this method on a module. And so to define a module, we use a PyModule def, kind of like a PyMethod def. And this specifies some arguments for, or the parameters for creating this module. So the PyModule def structure starts with a macro PyModule def head init. And this initializes some internal state that Python will manage. It's not really important to know what that is. I don't actually know exactly what it does, but you should just always start with that macro. Then it takes the name of the module as a C string, and this is the module's name as it will appear in Python. It takes a doc string, and again, we use pydoc_strvar to define this doc string so that you can disable it at compile time. It then takes the size of a global state structure, which we don't have any global state for our modules, so you can set it to -1, which says, I have no global state, don't allocate any extra space for me. It's not super common to have global state, and there's a lot of extra stuff that you need to do when you have that. So this tutorial will not cover that, but it's safe to just set that to -1 and you have no state. Next, we have a null-terminated array of PyMethod def structures, and these are the free functions that will be defined in this module. So we've changed up our def a little. We have the PyMethod def from before, and then we have an empty structure, null. This array needs to be null terminated, so you don't pass a count of how many methods you have. You just also pass an empty PyMethod def, and that's how the module knows where that array terminates. It's kind of like a null terminator in a string, but for fancier objects. And then after that, we have a bunch of function pointers which manage the global state, and since we don't have any, we can set them all to null. Great. So we still don't have a module object yet, or anything that we can import. So we've got this structure. It defines how to create a module. We've got the structures that define how to create the functions, and we need to actually create the module object so that we can import it. And the way you do that is you define a function of type pymod initfunc in your shared object. And this function needs to have a special name, which is pyinit _ and then the name of the module. And this name is very important because it's how the interpreter knows how to initialize your module when it finds it in the import path. So for example, our function is going to be called pyinit _ fib because we have the fib module. And that name needs to match the string that you put in your module def. So in that module, in that function, we need to return a new module object. And the way we do that is with the function PyModule create, which takes the address of our module definition, or our module def, and returns the new module object. So we don't have any initialization in our module, so we can simply just say return PyModule create fib module. And this file now can be imported from Python once we've built it. Does anyone have any questions up to here? Awesome. So right now we just got a C file, and we still have not actually compiled it. And we need to compile our C program ahead of time so that we can actually run the code. So the way we're going to do that is we're going to use setup tools, which is the standard tool for packaging Python projects. And setup tools also has a bunch of things to help us build our extension. So we're going to start with a standard setup.py. So this doesn't know about our C extension yet. This is just what like a normal setup.py looks like for anyone who's not familiar. The only difference is that we've got one extra classifier. And this classifier says that this project only works with CPython. So an important thing to know is that if you write a C extension module, unless you go and do extra work, which we're not going to cover in this tutorial, you cannot run your code on PyPI or Jython or IronPython. You are restricted to using just the CPython interpreter. There are tools that let you get this compatibility, but you have to do extra work to get that to work, so it's not the default. So this classifier doesn't actually do anything. It's just information for humans. When they go to install your module, they know, oh, this only works with CPython. So now we need to extend our setup.py to tell it about our extension modules. And the way we do that is we import the extension class from setup tools. And then there's an argument to the setup function called ext modules. And this is a list of all the extension modules to build in our project. So this says that we need to build the module fib.fib, because it's the fib module in the fib package. And then we pass a list of all the C files which are required to build this module. And we only have one, so it's just fib/fib.c. And these paths are relative to the setup.py. You can, at this point, also pass a bunch of extra things, like you can pass include dir options, link dir options, arbitrary compiler flags, and so on. But the default configuration that the extension class gives you is it will put the proper Python include dir in the include path, so that you are linking your in the link path. So you will always be building your extension for the Python version that's running the setup.py. And then, so now that we've got this setup.py, you can invoke this by just running python setup.py buildxt, and then the in-place flag says move the compiled binaries out of the builder into the package so that they're importable from from the root of the repo. So at this point, I'd like to have everyone actually run that. So if you cd into exercises/fib and run python setup.py buildx in place, just to make sure that everyone's environment works so that we can move on from there. And if that runs successfully, meaning it doesn't tell you it failed, then you can try opening up IPython and playing around and seeing that the function actually does what we think. So if anyone's environment is not working, I can come help you now. And yours is not working, so. The setup end script should activate it for you. But if you deactivate it for some reason, then yes, you need to reactivate the virtual environment. Okay.
I don't have Python set up.
So
The error message, I think that's the error message.
yeah, no, it means that Python didn't compile for some reason above. So
Up, down.
Sorry.
VI keys,
Luckily arrow keys work, I think.
yeah.
I use Emacs personally, so
Different religious war.
yeah. Whoa, this is paging interestingly. Interesting. Can you install nptd in your virtual environment and just run npd? I think the issue is that the clock is wrong, and so it's not actually building Python because the makefile thinks the files are new enough. Does that make sense?
Okay,
So in
just go and clean make Python.
yeah,
That also solve the problem.
yeah, assuming everything isn't like totally out of date.
Okay, so where's the Python that you have?
Submodule / CPython. So you'll want to run, actually if you just open the setup env script, you can just see the commands. It's very simple for Linux. It's just like /configure with pydebug and then make, and I did make J4 just to make it a little faster. So if you just want to run those commands,
Sure.
and then we'll see what happens. Does anyone else have any issues getting this build? Okay. Did everyone run it, or it's still building and we talked? Anyone not fall into those two categories? Cool. So we're going to do another build step. So if you didn't get to run this, that's okay. But just to move in the interest of time. So if we remember back the definition for our pyfib function, we had this call, pylong as unsigned long of n. And we just said, let's assume that this is an int. But we didn't actually enforce it in any way. So if in the REPL, why don't you try calling fib with something that is not an integer to get a sense of what happens. And the spoiler's on the screen, but you'll notice that it hangs and it doesn't return. And if you try to control C, it doesn't do anything because Python has registered its own signal handler, which catches sig int so that it can raise a keyboard interrupt exception. But it does that on the next bytecode instruction that gets executed, and we're stuck in a while loop in C somewhere, and it's never going to execute another bytecode instruction. So it just kind of hangs. So you can suspend your terminal with Control-Z and then run kill %1. So I wanted to have everyone run that at least once so they get a sense of the dangers of writing a C extension, because it is difficult, and these are the kinds of failure modes you get. Your terminal hangs and you can't Control-C to interrupt it. So the reason that this failed is that pylong as unsigned long expects that the argument is a long object, and we did not pass it a long object. We passed it a string or a dictionary or anything else. So it returned unsigned long of -1, which is unsigned long max, which is a very large number. It's this number, which we're trying to compute that Fibonacci number in a while loop. So it would probably terminate eventually, probably. I don't know how long that would actually take, but it would take a very, very long time. Yep.
Would you typically check the type at the Python level with another wrapper around this function?
That's one way to do it. I would advise against that because someone is going to import your internal stuff. Also, it's better not to assume preconditions for your function. But we will talk about how to handle this from within C. So, but yes, that is one option, is to enforce the types in Python first. So C, the programming language, does not have exceptions in the same way that Python has exceptions, or now C++ has exceptions, but they're not Python exceptions. So we need a way to represent Python exceptions from C. And the way that works is that, every function in C has exactly one return type, and there's no external way there's no exceptions on top of that. So the way the CPython API communicates exceptions is there are 3 global variables somewhere, which is the type of the current exception that's being raised, the value of the current exception that's being raised, and the traceback of the current exception that's being raised. And if no exception is being raised, all 3 of those values are null. So when you need to signal that a failure has occurred, your function must return some sentinel value that the caller knows about ahead of time. They check the value against that sentinel, and if it matches, then they know an exception is raised, and the values of the type, the value, and the traceback will be set for them. So this is similar to Erno in the C standard library and POSIX libraries, but it has a little more context because it has that type and traceback. So if we call a function and it needs to communicate an error to us, we have this sentinel value, and that sentinel value depends on the type of the return. So for example, if a function returns a PyObject pointer, then it can use null as the sentinel value because null is never a valid PyObject pointer. And in fact, it's never a valid pointer in general. So when we call pylong from unsigned long, there's a chance that we can't actually allocate this new long object because we're out of memory or something terrible has happened, in which case this function will return null, and it will have set the global exception state to a memory error with a value of a new memory error instance and an empty traceback because that's the site of the exception. So this is the most common sentinel because most of the APIs in the C or most of the functions in the CPython API act on PyObject pointers and they return PyObject pointers. This is also the sentinel value that you need to use for our method. So if pyfib fails, it will return null itself. For API functions that are semantically Boolean values, they use an integer instead of a bool type to return. And that's because they use 1 for true, 0 for false, and -1 for exception. So Boolean has no way to communicate failure. It only can communicate that it is true or false, so an integer is used instead. So there are CPython API functions that return ints, and many of them are actually semantically bool. Then there's the other category, and we've kind of seen this already. So pylong as unsigned long needs the entire codomain of the function. It needs to, any valid unsigned long could be returned from this function. So there's no single sentinel value that they can use. So instead, what this function does is it returns something if it fails, but it just sets the exception counter, or the exception indicator. So the programmer must always call occurred to see if an exception has been raised after this function, because any return could be a valid return. So the function to check to see if an exception is raised is occurred. This returns the pointer, which is the type of the exception that's currently being raised, but is almost always used in a Boolean context. Even the name implies that. So an important thing to remember about reference count, about exceptions, is that you still need to manage any references that you own. So if an exception occurs, you might already own some objects, and it's your responsibility to decref all of them and to clean up any of the resources that you're currently using. So a very common pattern that you'll see in the CPython code base, in NumPy, and any large C extension module, is to have an error block which has a bunch of PyDecrefs in it. And if you ever fail, you just say go to error, and it will decref everything and then return null. And I know a lot of people have learned that goto is intrinsically bad, but that's not true in large C code bases. Gotos are used mainly for resource management in this way. So we know how to propagate errors by just checking the sentinel and returning our sentinel. But if we want to raise our own exceptions, we can use functions setString or format. So these functions, setString takes the type of the exception that we want to raise, and then a string as a C string, which is the message for that exception. And format is similar. It takes the type of the exception to raise and a format string, and then arguments. So this is more like a printf format string, so you can provide context. And I would say that you should almost always use format instead of setString. And that's because if you're raising an exception, it means something is wrong, and you at the call site, at the raise site, have context about the failure that you can give the user. And it's a lot harder to debug your C extension modules. They can't just step through it in PDB or use their standard tools. So you want to make the error message as informative as possible. Don't say n was negative. Say n was negative. This is the value of n, and allow people to know that. So try to use format as your default exception raising. Then there are some helpers for very trivial errors. For example, no memory raises a memory error. There's not a lot of context you can give with a memory error. It's just, I don't have RAM to allocate this. So I mentioned that the first argument is the type of the exception to raise. The C API provides all of the built-in exceptions as globals, which under the namespace PyEXC_name, not to be confused with PyERR, which is the prefix for setString and format. So for example, PyEXC index error is a reference to the index error object, which is built into Python. PyEXC value error is the value error object, and so on. So now to actually write some new C code, let's add error handling to fib so that if we get past an argument that is not an integer, we raise an exception instead of just failing or doing something. Hey, so you tried some stuff? Were you able to get the...
I tried to clean Python, which didn't work. Now I'm installing NTP, which is going slowly, but go.
Okay, sorry about that.
No. I understand. Still learning from listening, even if not doing it.
Okay. Were you able to get your environment working? So everything's working now?
Yeah.
Great. Does anyone still not have their environment working? Yeah. Okay. Okay. Cool. Sorry about that. Okay. If anyone has any questions during the exercise, I'm here to help. Okay. So we know that if we, so the reason the code failed, if we look at our as unsigned long call, is that we gave it an argument that's not an integer, right? And so that means that pi long as unsigned long. Well, so it'll never be a negative. Yeah. So that's one way to do it. But we also know that it will have raised a Python exception. So kind of like following a Pythonic approach, you would say, try to run the code, and then if an exception is raised, let that exception propagate up. So so no try catch in C, but we know that if we just call this function, it will have set the global exception indicator for us, and we can check that indicator. That was a PyEr occurred. Just ERR, sorry, not PyError. The API is a little like terse here. Yep. Does that make sense? Cool. Also, in the fib directory, there are answer keys for the exercises. It's like fib hyphen something. I don't remember. I think it's like fib error.c or something. If you have something that you think works and you want to check it. Does anyone have it working? Cool. Yep. They're next to the file, so it's in the fib directory. There'll be like fib hyphen. I think this one's error.c. Error handle, yeah, and that is the answer key for this. Great. Are people still working on it? Question? Just run the buildExt command again. So Python setup.py build underscore ext hyphen hyphen in place. The build command from before. So yeah, the same one. There is a function PyR exception matches, and so the current thing is PyR occurred. That gives you the type of the current exception that's being raised. But if you wanted to like catch the exception, you should use. Yes, it actually returns a pointer to the type of the exception. Yeah, and there's Py. Yes, and there's PyR fetch, which takes 3 references, and it will give you the type, the value, and the traceback.
But when Python itself is going to give you a type, so if it gives you a type error, for example, and says an integer is required.
Yep.
Right. How do I get the string an integer is required?
Yeah, so you can use PyR fetch to get the value, and then it's just an object, so you would call stir on it or whatever. However you would get the message from the exception type. And how to call stir we'll cover in a second. Anyone still working on this? Or has everyone completed it? No? Do you? So that's one way you could do it. But maybe the more Pythonic way is to just try to run the code and see if it raises an exception, right? Like in Python, you don't like do checking ahead of time. You just run it, and if it fails, and you let that failure happen. Does that give you an idea? Okay. So for example, so actually we kind of can stay totally in the pyfib space. So we know that if we call this function and it doesn't work, it's going to raise an exception, right? So what we can do is say, run the function, and if it failed, then propagate that error. Also, some people might have noticed already, there's an appendix in this which has doc strings for all of the functions and some information about it that you can read while going through these. PyR format. The format string is all the characters are in it. There's a link to it in the appendix for the docs for PyR format. So it's mostly like the printf ones, and then there's 3 special ones, one for calling stir on a PyObject, one for calling repr on a PyObject, and one for calling ASCII on a PyObject, which is the Python 3 repr that's ASCII compatible. That makes cool. Are you good yet, or no? Do you need some? So after we call pylong as unsigned long, an exception will be raised, and we can query that right if it fails. And if so it's not going to return null because pylong as unsigned long returns an unsigned long. So we don't need to know what it returned. We can just check if an exception was raised directly. So there's the function that checks if an exception is currently raised is pyr underscore occurred. And yeah. Cool. I think you're on the right track now. Okay. So I'm going to okay. Think everyone's there or mostly there. So I'm going to talk about what's called the abstract object API. So far we've talked about working with PyLong objects and unsigned long objects, and we're still in this very type-heavy space, right? We know that we have to have a long, or we have to have an int, and we're going to work with it as an unsigned long. But Python is a dynamic language, and that means that we can have things that respect the integer protocol, or we can pass around objects as long as they conform to some interface. We don't need to program against types, we program against interfaces. And we can also do this in the C API using this more abstract object API that we have. So there are some operations that we can do on any object regardless of its type. For example, we can always call repr on an object. That always works. So in the C API, there's a function PyObjectRepr, and this corresponds to that built-in. And we just give it a PyObject pointer, and it doesn't matter what the type of that is. It will always return to us either null, meaning that we failed to call repr, and an exception will be raised, or a new string object, or a PyObject pointer, which is the result of calling repr. There are other functions for all the built-ins. So we have PyObjectRepr. We also have PyObjectGetAttr, PyObjectSetAttr, things like that. And we don't need to know the type of the inputs. We just need to know that, we'll try it, and it works on these very abstract PyObject pointers. There's some trade-offs to consider. So because all of these functions are abstract and they act on anything, it means we need to determine what actual concrete implementations of these methods to call at runtime. So there's a performance trade-off that you're going to be making where you're saying, I can act on any type of object, but in exchange, I need to dynamically decide what code to run, and there's cost there. But on the other hand, it means you can accept any type of object that meets this interface, so your code will behave more like standard Python code. It will feel more Pythonic from a user standpoint. So one route that people go is they write very specialized code if they know the types up front with an equivalent abstract route, which is slower, but it allows the code to run at all. So as I was saying, we've got PyObjectRepr, which is this generic function. There's also getAttr, setAttr, and basically all of the built-ins are in this PyObject namespace. Now, again, not all of these will work, right? PyObjectGetAttr doesn't work on all objects, or PyObjectSetAttr doesn't work for all attributes, and in which case, the function will return an error saying, attribute error, this doesn't exist, or attribute error, you can't set this attribute. One of the kind of quirks of the API is if you want to compare objects, for example, greater than, less than, equality. Instead of having different functions for all of the comparison operators, there's a single function called PyObjectRichCompare. And this function takes the left-hand side, the right-hand side, and an enum, which is the operation to perform. So if we wanted to call a less than b as Python code, but from the C API, we would say, starting with a PyObject pointer a and a PyObject pointer b, and these come from somewhere, then the result as a PyObject pointer is PyObjectRichCompare of a, b, and PyLE, which says perform less than, actually, that's less than or equal to. PyLT would be less than. So little issue there. But so what this will return is the object, which is the result of a, in this case, less than or equal to b, as a PyObject pointer. And this is going to give us back a new reference to the object. So we are responsible for this result. So the first thing we need to do, check if the result is null. That's the sentinel value that says that this failed, and we know an exception has been raised. So we ourselves do whatever error handling we need to do, and then probably also return null, or return whatever our sentinel value is. Otherwise, we can use result however we need. And then when we're done with result, we need to remember to decref it, because we own this reference. Now this function can potentially invoke arbitrary Python code or arbitrary C code, because it's going to go find the less than or equal to method or the equals method off whatever the types are and figure out what to call. So it can fail, and we really need to make sure we remember to check for that. It's not just memory errors now. It can be type errors. A and B are not compatible, or they're not comparable, things like that. Because it's annoying to work with new references, we can mess up, get the reference count. There's a little helper in the C API called PyObjectRichCompareBool, and this function instead returns an int, which is the Boolean result of the comparison that we just did. So this returns either 0, meaning the comparison is false, 1, meaning the comparison is true, and -1, meaning the comparison failed. So if we rewrote our example of less than or equal to using this, we could say int result is PyObject rich compare bool of A and B. And now we just need to check if the result is less than 0, which means that an exception has been raised. And now we don't need to worry about a reference count on our result because we just have an int, and the reference has been dealt with internally to PyObject rich compare bool. The reason that you might actually not be able to use this is that you can't always call bool on the result of comparisons. For example, if your objects are NumPy arrays, then A less than an array returns a new array object. It doesn't return a Boolean. So there are cases where you actually need to use the full power of PyObject rich compare. We can compare objects. We can also treat them like numbers. For this is called the number protocol. So there are functions in here for add, subtract, multiply. Div is split into 2 functions. There's trueDiv and floorDiv, because in Python 3, those are different operations. And all the binary operators and unary operators and even ternary operators like pow are in there. For all of these functions, there's also an equivalent in-place version. For example, PyNumber in-place add or PyNumber in-place subtract. And this corresponds to the dunder I add or dunder I sub function. So the way those functions work is they still take 2 arguments, and they return a new reference to the result. The only difference is that the result is sometimes the same object as the left-hand side of the operation, but not always. For if in-place add and in-place subtract will always work if add would work, but if it could be done in place, it will use it. So for example, in-place add with integers returns you a new integer as the result. But in-place add with, say, a list will return a new reference to the same list because an in-place addition could be done. Yeah, so just like the abstract object API, all of these functions still act on just PyObject pointers and not some more concrete type. So while we can use the PyNumber protocol with long objects, we still just treat them as PyObject pointers because it is this more abstract thing.
I'm sorry, would you say that bit about the in-place operators again?
Yeah. So there are functions in Python like double underscore I add, double underscore I sub, and so on. And these get invoked when you say like A plus equals B. So the way those operators work, even from within Python, is that they return the new result. And that's true from C also. So they always return a new result. However, if the operation could be done in place, the result might be self, or it might be the left-hand side of the operator. But that's not always possible, right? Because, for example, strings are immutable. So if I say A plus equals B, that actually is going to create a new string and bind it to A, but it's not going to have mutated the old A in place. So the point there is that it is not safe to assume that the result of the in-place operations is the left-hand side of the in-place operator. But even if it is in place, you will still now have a new reference to the left-hand side that you own. Does that clarify? Okay.
So I guess I'm just, from the Python command line,
Yep.
you can't do a plus add of a string literal and a string literal.
Yes, because you can't assign to a string literal. But if you wrote like A equals a string, A plus equals a new string,
Yes.
A will be bound to the concatenation of that, but it will not have mutated the original string.
But the original string is gone at that point.
Okay, if you write A equals B equals a string, and you do A plus equals, B will not have been changed. But if you do that with a list, B will have been changed. Yeah. So actually, winding back, I think I forgot to mention that. So I said there was trade-offs, but one of the big advantages of using these abstract APIs is that Python has very good data structures that we can take advantage of. So the PyLong object is an arbitrary sized integer, and that's a very complicated data structure if you wanted to write it in C. So we wrote our CFib function to just use unsigned longs, but that has a very particular failure mode. Because they're fixed width, they can overflow. And with the Fibonacci numbers, they actually overflow very quickly. So as a exercise, we should rewrite the fib function to use the PyNumber API instead of converting to unsigned long objects. So here we're going to trade a little bit of the speed that we got from acting on native C types for correctness in that fib of n greater than 94 actually returns the right answer instead of just returning the answer mod the max unsigned long. And if you go through that quickly, you can do the thing we talked about before where you have a fast path. So if n is less than, I believe it's 94, you could use the C loop because you know that the answer will always be correct. But if it's greater, fall back to the slower Python route, which will still give you the correct answer. And the answers for these are in fib, I don't know, abstract or number or something.
So going back to your PyObject repr things earlier,
Yep.
that returns a PyObject, doesn't return a string.
Yes.
How do we get the string?
How do you get the string?
As an actual C string.
Yeah, the string object well, there's an API for working with string objects, kind of like how there's the API for working with long objects. So there's a function, PyUnicode as UTF-8, which returns a C string or null if it couldn't be converted.
So is that the way that I would get the actual name of a Python exception type, for example?
If you want the name of a type, you could get it from the type object instead.
Okay, so if I do the PyError occurred,
Yep.
right, that returns a PyObject.
That returns the PyObject pointer, which is the type. So you would be able to cast that to a type object after doing a type check, and then you could get the TP name out of that. We'll cover working with classes a little later, and we'll talk about getting that name. Though, if you wanted to catch it, better than checking the name would be to use PyError exception matches, which is actually what happens when you have an except block, because it does subclass incorrectly. So, for example, if the exception is a value error, or if I want to catch all value errors, and the actual exception raised is like my value error, which is a subclass of value error, PyError exception matches will handle that for you.
I was trying to do something too, where right now, if you pass something that's not an integer, you get, and raise the type error as a, integer required.
Yep.
I wanted to change the string integer required to integer required, you gave me X,
Yeah, yeah.
right?
Yeah, so this is a case where actually internally they're using PyError setString, and it's unfortunate because you don't see the value that you got. Were you able to
Yeah, so
get it running?
I got the environment built now.
Okay, great.
Yeah, so
Cool.
I just fiddled with
Okay,
try to we've got the loop where I had to kill it.
nice, cool. Yeah, do you have any questions on like anything you missed while you were out there? Because I think I resumed kind of quickly.
I'm just gonna try to go quickly through the chat.
Okay, cool. If you have any questions, let me know.
Awesome.
Does anyone have any questions or need any help? Does anyone have it working yet? Yeah? Cool. Didn't notify.
Is that the best way to do that, or is there a better way?
Yeah, no, that's the right way to do that. Okay, so this code works. Awesome. Though, there's one thing you forgot to do, which is that, so when you call PyNumberAdd, you get back a new int, and you own this integer. You also own a and b, so you need to remember.
For returning.
Yep. And you know, if you think about this conceptually, you're like shifting over. So in the loop, you need to remember to get rid of all the temporaries that you're creating. Like to an unsigned long.
Yeah.
PyLong as unsigned long. You need to remember to check for a failure there. Everything.
Interesting rabbit hole I'm exploring, which is anyway, really need to get into that yet.
Okay.
How come here you do touch it more than here, but in this case you're doing the PyAR code?
So this is because PyLong from unsigned long returns a new PyObject pointer, So yeah, so that's as unsigned long. So there's no sentinel or good sentinel to check for as unsigned long, but for from unsigned long, we know if it returns null, it has to have failed. So it's kind of a difference. It's just that there's a good sentinel value for some. Pi or pi long as unsigned long is kind of a special case in that there's no good sentinel to check.
But you could still PyTorch occur in this case?
You
or no?
yeah, that would totally work also.
I ended up making a copy so that it wasn't shared between Windows and Linux,
Yeah.
and that may have made the timestamps work better.
Okay.
Because that is, it now is making progress.
I see.
Either that or the Python directory and the Python executable with upper versus lowercase. Something about
Oh,
the
you know
processing,
what?
I think, is
Yes,
weird.
that's what it
That
is.
second
No,
guess
I know.
may be it.
Yeah, no. So what it is, if you so in the setup env, so that actually depending on your operating system, the name of the output is different because there's a directory in the Python repo called Python with a capital P. So on Linux, it compiles to a binary called Python with a lowercase p. On OS X and Windows, it compiles to a binary called Python.exe. Even on OS X, it actually calls it that. So I have two branches. If your uname is Linux, do this. If your uname is Darwin, do this, otherwise fail. I imagine uname for you is returning Linux, which means that it doesn't look for, so when it said it's a directory, that's because
was
that is
the error
actually
message, and
true.
that was the-
I just didn't, I forgot that on Windows it does that. So I guess what,
Linux VM, Windows host, but
so the
network
file
share.
system is still actually case insensitive. Or for some reason, so the way I'm detecting if you're on Linux is different than the way the makefile is detecting if you're on Linux because it's generating a binary called python.exe most likely. I see. So that error is still going to occur. So
No, because I copied it onto my Linux file system.
I see. Okay.
That's how I got it to
Gotcha.
return Linux.
Gotcha.
So if that didn't make it different,
Yeah. Yeah.
that
Okay.
was irrelevant.
I see. Yeah, but
I guess
that is actually a
this
very very
guess
big difference.
worked.
Cool.
So
Awesome.
Yay.
Yeah.
That may be a change in the future.
Hey.
If I have a pointer to a Pi object, how do I actually give it a value? I don't think that's right. How do I?
Yep. So you, in the same way that we called pylong from unsigned long, with arbitrary values, you can just pass it a literal. So you can say like a is pylong from unsigned long of 1.
Wait, so you call this?
Yep.
Oh,
Right, because that gives us a new pi object pointer which holds the value of the argument.
oh, so I just put in 1?
Yep.
There? Oh,
You can just give it a.
I thought, it's overloaded, so it can either take a Pi object or
No.
a number?
No, n here or whatever c is.
C is a.
It used to be a
Pi
unsigned
object.
long, though. Remember? So that yeah. So it actually needs to take an.
Oh, really?
Yeah.
Googled it. Yeah.
Actually, it's in the appendix of the docs, so
Oh.
you already have it locally. Yep. So if you look up like pylong from. So as unsigned long and from unsigned long are different.
It's a Pi object.
That's as unsigned long. And then the other one is from unsigned long. So it's the two different ways, going
Okay,
from a
so-
pi object to a long and going from a long to a pi object.
Oh, okay.
Does that make sense?
I think so. So here I could say from unsigned long.
Yep.
to give it a- okay.
So I'm looking through your solution,
Yep.
and I'm curious, why are you decrementing A every time
So what happens is that C is when you call pi number add, you get a new reference to an integer.
Okay.
So you own that object and you need to manage it. So if you think about what that loop is doing conceptually, you've got like A, B, and C, and you're shifting down one.
Okay.
Like constantly, like so you, there's like really like a sliding window over all the Fibonacci numbers.
Okay.
So when I shift down, or if you look at the next line is A equals B,
Right.
which means we're going to lose whatever A used to be bound to, which means we no longer need it because no one can reference it. So we need to remember to give away our ownership of A before we get rid of it. Otherwise, we'll be leaking an object every iteration of the loop. And then when we're about to return, we just do it again.
Okay.
Because at this stage, it's still valid. We still have an A.
Right.
We have an A and a B, and C is an alias for B at that stage.
Okay.
That make sense?
Yes, it does.
Cool.
So, thank you.
How come you never decref B?
Because so the way this loop works is we've got A and B really, and we want to shift it over. So and then assign a new B, right? So C is just a temporary name, but really A and B are the two important things. Yeah. So when we shift over, so we've got an A and we've got a B, and we shift over, and we're about to lose. So it means we're going to lose whatever A used to be, right? And that's what happens here. So then we decref the old A, then we do the substitution to shift it over, so B becomes A. So then the next cycle of the loop, we'll decrement what used to be B, but is now called A. And then when we're at the very end of the loop, we just need to get rid of the very last A, and then we return B, because we can't just get rid of it, because we got to give it away to whoever called us. Does that make sense? Cool.
Do I need to increase the reference on my arguments?
No, you don't. So arguments are owned by the caller, so you don't own them. So you don't increment. You only increment them if you want to take ownership. So for example, if I was a function like list append, right? Then list append takes ownership of the argument, so it increments it. But otherwise, you don't need to increment or decrement.
But it can disappear while my function.
It can't disappear because the lifetime is strictly greater than your function's call.
Kind of fun. I changed it so that if it's a positive number, you give it, it uses the long version, and if it's a negative number, it flips it and uses the
Oh.
wraparound version, so you can compare to see what they do.
Nice. Oh, I see. So if you give it a very large number, then it, yeah, interesting.
I gotta figure out to put it in the garbage collection.
Okay. Hey.
I get rid of 0.
It hangs. Interesting. So let's look at what your implementation is. So this is still the CFib. So this is not the abstract stuff. Okay. Gotcha. Can you scroll back up? So you get it 0. It's just because it's actually one indexed fib, but instead of 0 indexed fib. So, I actually never. Oh, wait. So, yeah. Yeah. So maybe you had an issue in. Yeah. Yeah, maybe. Okay, cool. Yep. Okay. still working on this, or should I move on to the next section? We actually have like 10 minutes before the break, so I can introduce the next topic. So I'm going to do that. Cool. So, as was alluded to, right now we're just using right now we're just using this meth_o flag, which means our function can accept exactly one argument, and its type is PyObject pointer, and it's up to us to do any conversions or checks that we need to do. But Python allows us to have much more expressive signatures in our functions. We can have more than one argument. We can have 0 arguments. We can have optional arguments and keyword-only arguments. And all of these are also possible in the C API. So the first way that we can express more complicated arguments is by changing the meth_o flag that was passed to the PyMethod def structure to meth_var_args bitwise or with meth keywords. So it's a bit mask. So using bitwise or says give us both options. So it's actually like it's var_args and var keywords, and keywords. So when we change the flags to this, we need to change the signature of our C function. So the wrapper function. So pyfib's signature would now it still takes self as a PyObject pointer, and now it's passed args and quargs. So args is a PyObject pointer, which is a tuple of all of the positional arguments that are passed. And quargs is a PyObject pointer, which is a dictionary of all the keyword arguments that were passed, with the caveat that if no keyword arguments are passed, quargs may be null. The reason, it might also be an empty dictionary, but it could be null. So the reason for this is that it's much more expensive to allocate an empty dictionary than it is to allocate an empty tuple. So it always allocates a tuple, but if no keyword arguments are passed as an optimization, the dictionary won't be allocated at all, and you just get null. So you need to know to handle that, and that's still a valid state. So when you use just these flags by themselves, you basically have a function that's equivalent to def f of self, star args, and star star quargs from Python. The stars here are very different from the stars in C, but I think we get the idea. So this gives us the most control over how we parse the arguments, but sometimes being very flexible is also very hard to work with. Because if we just had to have this args tuple and this quargs dictionary, we wouldn't know what to do with it. So instead, the C API has this function pyarg parse tuple and keywords, which takes the args tuple and the quargs dictionary, knowing that the dictionary might be null, and it allows us to parse the arguments out to match whatever signature we want. So the way this function works is it takes args and quargs, and then it takes a format string, which specifies the types and the amount of arguments that we have. And this format string is kind of like a scanf from C. And then it takes an array of strings, which are the names of all of the arguments, so that you can pass them by keyword, followed by references to all of the basically places to store all of the arguments once they get parsed, if they get parsed correctly. And then this function returns a Boolean value, which says whether this successfully parsed the arguments or not. And if it returns false, an exception will be raised. For the values in that format string, the simplest value is the O format character, which says accept this as a single object. So if we wanted to rewrite our pyfib wrapper using pyarg parse tuple and keywords instead of using meth_o, we would first start by declaring a static array of keywords. In C, static local variables are basically just global variables that are names that are scoped for this function. So only within pyfib can we access this variable, but it's only initialized once. Then we declare storage for n, which is the argument that we want to accept. And it's not initialized because we don't know what the value is going to be yet. Then we call pyarg parse tuple and keywords and feed it the args, tuple, quargs dictionary, and this function knows that quargs can be null, so that's okay. Then the format string, in which case we're passing O, which means we accept one argument and its type is PyObject pointer, so perform no conversions. Then the array of strings, followed by the address of n. So this is where to write the result of the object argument if it parses successfully. And if it fails, then it means that for some reason the call site does not match this signature, and we just return null, and an exception of the appropriate type will be raised. And otherwise, n will have been bound to the argument passed as n, and we can proceed. Also, it's a borrowed reference, so just like in meth O, how you didn't have to manage the ownership of n, you don't have to manage the ownership of n in this case also. So what we get by writing this is the caller from Python basically treats it the same. They just get to call fib. The only difference is they can now pass fib by keyword, so they can say fib of n equals whatever value they want. Also, yeah, we had to update our method def, so now instead of meth O, we pass meth var args and meth keywords. Okay. We got a break in 5 minutes, so I'll try to cover this quick, or just the start at least. So we had that O format string, which says pass an object with no conversions, but instead of forcing the user to always do the conversions themselves, PyArgs, parse tuple, and keywords provide some helpers for this. So another simple converter is the I format character, which says accept an argument as a PyLong object, or as any object which can be converted to an int. So just call the int function on it, and then return to us the cint value. Yeah. So for example, if we wanted to write an add function in C that added two integers or integer-like objects together, we could, we start again with our array of keywords, and here our arguments are called A and B, and then we end it with null to say there are no more arguments. We declare storage for A and B, again, uninitialized. And then we call PyArg parse tuple and keywords with our args quargs. And now this format string is II, which means we have two arguments, and both of them are integers. Then we pass the addresses, the keyword array, and then the addresses of A and B. And the order of these are important. The address of A corresponds to the first format character. The address of B corresponds to the second format character. And so this function gives us two integers. We can add them together and then return PyLong from long. So this is just like binary plus for integer objects. But, yep. So the user does not have to pass them by keyword. So it reads the positional argument tuple and the keyword dictionary tuple and does the same algorithm to resolve arguments as Python normally does. So that's basically like writing def in Python, def add of self A and B. So you can call it however you would call it from Python. And it also does all the error handling to make sure there's no conflicts between the positional and keyword arguments. Actually, I show that right here. So when you've written add in this way, that add function from before, you can call it with two positional arguments, and that works. It will fail with an appropriate error message if you pass it a float. So it'll say an integer argument is expected, got float. Again, it's very frustrating because it doesn't tell us what the float was, but at least it's kind of close. We can call it with keywords. It will fail if you pass too many arguments with a good error message. It will fail if you pass a duplicate argument. For example, here we've passed A positionally, and then we also try to pass it by keyword. And it will, it allows mixed calls also of one positional, one keyword. So this basically just gives us parity with what we can do in Python, but for our C functions. And then if you notice, all these error messages use the word function, just like function takes at most two arguments, function is broken for some reason. It's kind of hard to understand when you're looking at a line with maybe multiple function calls on it, which function is broken. So the PyArg parse tuple and keyword format string can also tell the name of the function. So you put a colon at the end of the function of the format string, and everything after the colon is the name of the function to use in error messages. So for example, we can change our format string to II:add, and now the error messages will look like add takes at most two arguments, 3 given. And we now have a little, oh, yeah. No, we'll talk about keyword arguments are expressed in the format string, but we have a quick break now, so we'll cover more types of arguments after that. Yeah, so I think there's like food and stuff, like 20-minute break or 10-minute break or something. second, let me just close the door. Just gonna close the door. Okay, so we left off a great cliffhanger about keyword-only args and optional args and things like that. So just a refresher, going through pyarg, parse tuple, and keywords, and the format strings, and different ways you can define signatures for your C functions. So, yep. So this is actually, so it's not macro, this is itself a function, but this will be slower for the simple case, I guess you could say. Like for meth-o, that's pretty fast, because all it does is assert that it takes the dictionary. Let me step back. So meth-o is implemented sort of in terms of this a bit. Like all functions actually take args and quargs. When you pass meth var args and meth keywords, you just actually get them unchanged. When you pass meth-o, the code that invokes your function does the checks for you. So you have to pay the cost no matter what, right? Meth-o still needs to check to make sure you only passed one arg and that you pass no keyword args. That's kind of a profile thing. I'm not sure which is like what the trade-offs there are. I would intuitively believe it's a little faster, but as soon as you want to add a second argument or an optional arg or pass it by keyword, you then have to go to this. So yeah, I wouldn't exactly advise writing the fib with exactly one argument using this, but yeah. Does that answer your question? Cool. Yeah, so Python, when you write a function in Python, you can write optional arguments, and you can also do that with pyarg, parse tuple, and keywords. And the way you do that is with a special character in the format string, which is a pipe. So everything following that pipe character is optional. So if we wanted to add a default argument to our add function, so that if you didn't pass a right-hand side, it just defaulted to 1, you could use, you would now initialize B to 1. So A is still uninitialized because it's a required argument, but B is initialized to a value of 1. And now our format string changes to I pipe I. So the first I is the first argument, and it is a required argument. The second I follows the pipe, so it's optional. And we then pass everything as before. What happens when an argument is not passed and it is optional is that the value at that of the reference there does not change. So for example, if I did not pass B to this function and it's optional, then pyarg, parse tuple, and keyword succeeds, but it does not write a new value to B. So in this case, it will hold on to the value that we've initialized it, which is 1. You can use the pipe for any other format character. So for example, we could have an O follow this if we wanted to. And in which case, it's still uninitialized. So you probably would want to initialize that value to null. And this is really important because if you just left it uninitialized, there's no way to know whether the value was actually passed or not. Yeah. So now we can call our function using that optional. We can call add of 1 or add of 2, and we can still explicitly pass this optional argument. We can get to like add of 2 and 2. And also, Python 3 adds keyword-only arguments to the language, and you use a $sign format special character. So all arguments following the $sign must be passed by keyword. So this is like a single star in a function declaration in Python. And this can also be mixed with optional. So if I have the format string $sign I, that means I have 2 required arguments. They're both integers, and the second one must be passed by keyword. But I can also use like I pipe $sign I, which means I have 2 arguments. The first one is required. The second one is optional, but it must be passed by keyword. And now, as an exercise, add optional arguments for the seed values of A and B to fib. And you can feel free to either do this using the abstract API, which is a little trickier, or the or just using the longs again, like from the original example. Feel free to use so the abstract API link is there. Also, the docs for PyLong, or sorry, PyArg parse tuple and keyword have all the values for the format string if you're interested. There's one warning I'd like to make. You might, if you look, you'll see that there's no formatters for unsigned integers. Those actually do exist in the official docs, but they don't do overflow checking. So if you pass negative integers to them, they just wrap. So they're unsafe. And I would suggest that if you wanted to accept an unsigned integer, that you should accept it as the O formatter and use PyLong as unsigned long, like we did originally. Even though they're there, they're easy to use incorrectly. Yeah, so that's kind of correct because the extension passes all of the extra link and include time options. Yeah, so this is still the right way to do it. Though those are the answer key files. So have you been editing those? Oh yeah, just check it. Yeah, so yeah, that's the correct way to build the answer key. Yeah, actually, you'll notice it when you run buildxt, it prints all the GCC commands, and they're like much more complicated than just simple GCC. Because what they need to do is say, so we just say include python.h, but it needs to know where to find python.h, and then it needs to know where libpython.so is, and also it makes sure that you compile your extensions with the same flags, because those might change how the object needs to get built. Yep. Yeah, if you want to accept them as ends, yeah. Yes. So if I believe it will call like the int method on it, right? So if you give it something that can be converted to an int, it will do that. But if you give it something that can't be converted to an int, then it will fail. Actually, probably uses the index method, not the int method. Right. So floats will fail that. still working? Sure.
It says, is there,
Did you update the flags for your function? From meth O to meth vars?
no,
Yep.
thanks.
Cool. That is an O. So, yeah. Which is for, sorry, for,
Object.
yeah, yeah.
So, I mean, this should take any object and then an optional integer, right?
Yes.
So I pass it a number. Why am I getting a bad argument in here? Function.
Did you update the flags on your function from meth var args to? So instead of metho, you want meth var args or meth keywords. Or meth keywords, yeah. Yeah, sorry, bitwise or. And now, if you run this. Wait.
I tried to do this recursive. I'm not saying just throw it and do it, but so I tried to do this recursively.
Yep.
What's going on here? Am I going to get a segfault here because I'm not deallocating?
So it's not going to segfault. It's just so there's two problems with nesting expressions in the C API.
Okay.
The first problem is there's no way to clean up the object that you get back. The second problem is you can't check if it failed. So you can't pass null to I think was this add, right? PyNumber add.
Yeah.
So you can't pass null as a second arg. So if PyNumber subtract fails, then it's going to segfault. And then the other issue is that PyNumber sub or subtract is going to return a new reference, and you need to deallocate that when you're done with it.
Okay, and that's why the one-liner. So if I were to pull this out, though,
Yeah.
I
So
would
if you would say like PyObject pointer temp or something, I don't know whatever you want to name it, is that, and then if temp is null, then you need to return null.
okay,
and
that's
then
how you catch the error.
Yeah.
So
And
would that still work then if I threw this in here?
Yep. But then you also need to say you can't just return here. You need to bind the results, and then after you get the results, you need to
Then,
decref temp.
all right.
Does that make sense?
Yeah, yeah, yeah. So, okay.
So
That would, okay.
yeah, this actually means this is kind of one of the reasons why writing C extensions like blows up the amount of code you have to write. Because while it would be great to write that nested expression, you have to check every single sub expression and deallocate every single sub expression. It gets very verbose very quickly. Yeah.
Damn. Okay. Sweet, man.
Cool.
Thank you.
Do you have a question? Cool. So then, are people still working on this, or should we? All right, I think we're gonna move on then. All right. So far we've talked about how to write just a single function, and we've seen a lot of things around just functions. But Python is object-oriented, and in Python we can define new classes, and we can also do this in C. I'd like to give another warning, just like I had at the start. Writing classes in C is super verbose, and really, there's a lot of work you need to do, a ton of boilerplate. I'd say try not to do it if you don't have to. So for example, if you are trying to optimize some code and there's one method that's slow, write the method in C as a free function and just call that from your Python method. Or even if there's 5 methods that are slow. Unless you really need to write a class in C because you need a very performance critical data structure, try not to do that. So assuming you know the warnings, I'll say, just as a final warning, a 10-line Python class can turn into 500 lines of C to do the same functionality. So this is why I really mean it when I say just try to write the minimal amount of C that you need. But assuming you know all of those warnings and you still decided that you need to write a class, I'll teach you how to do that. So I'm blowing through this quick. So a class in Python is also an object. So it's going to have a type, which is type, and it's going to have a ref count. And what a type represents is a couple things. So it represents how large instances need to be, and it tells us how to perform all the behavior. So it has all the methods, and it has the size of each instance. So when we have a PyObject, the abstract thing, we've got the obtype field. That points to our type. That tells us how to do everything. Yeah. That's worded. OK, sorry. So if we take a simple Python expression like repr of object, we can boil that down to a C API call, which is PyObject repr of that object. And the way this function actually works, this code is taken from repr. There's a little bit of error handling on top of this, but it's basically PyType of ob, TP repr of ob. So what it does is it says look up the type of the object as a PyType object, and then get the TP repr slot. And the word slot is an alias for field of a structure. If you think of structures as like tuples, slot kind of makes sense. And that is also the term that CPython uses for these. So if you look up the TP repr slot out of our type object and call that function on the object, that is the implementation for repr for objects of whatever PyType of ob is. So the type object defines slots for all of the behaviors that you might want to define with magic methods or dunder methods. So for example, the Python method dunder getattr is equivalent to actually that's get attribute is equivalent to PyType object.tp getattr_o. The reason it is O is that there used to be a slot called tp getattr, which took a C string as the name of the attribute to look up, which has since been deprecated. So the new one is getattr_o, which takes a Unicode object. There's tp setattr_o, which is similar, but this is for setattr. There's also a slot, for example, dunder call. It has a slot called tp call. And there are all of these for most of the built-ins that we've seen. So that works for all of the functions that we know about ahead of time. And there's not that many of the built-ins. I mean, there's a lot, but there's still a finite number. But in Python, we can also define arbitrary methods and give them whatever name we want with whatever signature we want. For example, we have a Python class which has a method repr, and it has a method with whatever name we want, in this case, also method. We know that we can store the repr in that TP repr slot, but where do we put the method? So there's a special slot called tpdict, which is a Python dictionary mapping arbitrary names to arbitrary values, functions. So this is actually the dunder dict of the type object itself, if you think about it in Python terms. So basically, we can just think of a type as a virtual method table or a bunch of functions that act on whatever this type is. So that's all the behavior, but we then also need to store values. And we store the values on the instances themselves. So the way you can define a new a type's instance layout, or the structure that holds instances of this class, is you make a new struct in C, and the first member of that struct needs to be a PyObject value, not a PyObject pointer. And this goes back to the idea that you can always cast a PyObject pointer to your struct because it's a pointer to the first member, or go the other way and take a pointer to your new structure and cast it to a PyObject pointer safely. And by starting our struct with a PyObject, we have a field to hold the type with the ob type, and we have the field to hold the ref count. So that gives us the data that's needed to be a Python object. And then after that, we can put whatever we want. And that will be the instance data that is on our class, our new instance. And this can be a mix of Python level values or C level values. So as an example, we can define a struct in C called myObject. And the first member is the base. So this is the data required to be a PyObject, and to be a Python object. So then we have a list field, which is a PyObject pointer that could point to a PyList object or a subclass of that. Then we have a PySizeT field, which is whatever, and we have a C-string as a const_char pointer field. So this means that our instances have these attributes available to the functions defined on the type. So there are a few slots that don't actually have a Python equivalent. So tpcall has dundercall, tpgetAtterRow has dundergetAtter, but there are a few that you can't override from within Python itself. The first two are tpalloc and tpfree. So tpalloc is the actual memory allocator used to create new instances of this class. And tpfree is the pairing function to deallocate objects allocated with the tpalloc function. So when you call the dundernew of a class, which is the tpnew slot, the first thing you need to do is actually allocate the new instance in memory somewhere and get a new pointer to that. So normally in Python, we would just call object.dundernew, probably through a supercall, but in C, we can actually control how that object gets allocated. I would say that you almost never want to override these values because Python has its own memory allocator that's optimized for small-ish allocations that are about the size of a PyObject. But if you're core to the idea of the class you're defining as allocation, you can override that if you want to. The other slots that don't really have a Python equivalent are slots used to support the garbage collector. So before I said that Python has a reference-counted garbage collector, where as soon as the reference hits 0, that gets deallocated. That's true, but there's a little bit of extra work that happens because objects can form cycles. So if object A points to object B, or owns a reference to object B, and object B owns a reference to object A, then there's no world where those reference counts hit 0 because they both own each other, so they both have at least one. And then that cycle can become stranded, where no one else has a reference to A or B. So those objects are actually dead, but they're keeping each other alive. So CPython has a cycle detector built in, which runs after a certain number of objects are allocated, which tries to identify these cycles that are stranded and clean them up itself. And when you write a new class in C, you can support this by defining a slot called tptraverse and tpclear. So the traverse function gets past a callback, which you need to invoke on all of the objects you have a reference to, which may be participating in a cycle. So if we think back to our myObject struct, one of our fields is a list. And lists are mutable, which means that someone could put a reference to this instance in that list. So we can now participate in a cycle. So our traverse function would need to call the callback on this list field. And what that callback does is different in different contexts, but just know that it's controlled by the interpreter, and we just need to invoke it on at all of those locations. However, if we had another field that was, say, a PyLong object field, we would not need to traverse that field because a long object cannot own another object, so it can never participate in a cycle. It doesn't hurt to traverse it because that object will just end the traversal, but it would be slightly more efficient to not traverse any of those objects. So it never hurts to traverse things you don't need to, but you can sometimes get rid of a traversal. The other slot that supports the garbage collector is tpclear. And this is how the interpreter can actually destroy the cycle. So if we have a list that has a reference to a list which has a reference back to the original list, so A points to B, which points to C, which points back to A, sorry, then one of the objects will get selected to be cleared. And that says forcefully drop all of your references. So in the case of a list, this will actually call like list.clear, and it will collapse the list back to an empty list, which will decref all of the members, which then recursively will decref the original list and will gracefully destroy the entire cycle. So the tpclear is optional. Even if you can participate in a cycle, you may not be able to drop your references and still be in a valid state. So part of collapsing the cycle is that it's going to be decrefing all the objects in order. And in the process of decrefing, we might invoke more arbitrary Python code, which was defined as dunderdel methods, which means that someone might still be able to get a reference back to the object that's in the cycle that's being destroyed. So we can't just call decref and deallocate all our members. We need to stay in a valid state. So for lists, we can do that. We can just shrink to an empty list. But for tuples, which are immutable, we can't drop our references and stay in a valid state. So a tuple would not define a TP clear, even though it would define a TP traverse. The reason that this is safe is that if basically it means your object is immutable, and if you have immutable objects, you cannot have a cycle which consists solely of the immutable objects, because you can never create the cycle in the first place. So for example, you cannot create a cycle of exclusively tuple objects, because you can't mutate the tuple. So it means that somewhere else in the cycle, there must be a mutable object which has defined a TP clear, and that object will be selected to destroy the cycle. Does that make sense to everyone? Cool. Then another slot which has no Python equivalent is basically the miscellaneous Boolean arguments that a type can have, and this is the TP flags. So this is a bit mask of binary options for the type. So one of the bits represents PyTP flags have GC, and that says that our object participates in this in the cycle detector, and that we will at least have defined a TP traverse and maybe defined a TP clear. There are a few other flags for doing subclass checks. For example, PyTP flags long subclass marks that this type is a subclass of PyLong object. There are a couple others like tuple subclass, dict subclass, and Unicode subclass. And these are to do very fast is-instance checks for the core types, which are done a lot in the interpreter. You don't ever manually set these. They'll get set for you when you ready the type, which we'll talk about in a second. But you can query for them once you have the type readied. When you define a new type, you should always start with a value of PyTP flags default, which is whatever needs to be there for default. I think it's either all zeros or a couple zeros with some compatibility options turned on, which allows them to like smooth transitions when they change these flags. So you start with that, and then you always bitwise or in all of the options that you want to add. Oh yeah, another important flag is PyTP flags base class. So when you define a class in C, by default, you cannot create subclasses of this. So I don't know if anyone here has ever tried to create a subclass of the type of a function in Python or like type of lambdas. You can't actually create this subclass because Python won't let you, and that's because this flag is not actually set. So the reason for this is that when methods call other methods, if they never assume that someone will make a subclass, they can statically resolve the address of those functions and then just call them directly. So it's more efficient. But if you want to support subclassing, you always need to virtually decide which, or at runtime decide which implementation of this method to call. So by default, you can just assume no one will ever override any methods, so I can call them statically. So it's a lot more work to make a class subclassable. And this goes back to deciding whether you even need a class in C in the first place. If you need a class in C, you probably don't need to support subclasses, but there are cases where you would want that. So to define a new type object, we start by defining the struct to hold our instances. So here is a class called Q. And so we define a struct which has the base, and we call this QBase. In C, often people will prefix their struct members, and this allows them to rename them later and add a compatibility layer with a macro. So because if I defined a macro called QBase, it might rename to something else. So it's a more unique identifier. This is why all the slots in the Python structures are things like ob type or TP flags. So we start with our base member, which is just the PyObject value, and that's going to hold our ref count and our type. And this is a queue with a bounded size. So we have a s size t for the max size, and we're going to say that -1 means that there's no max on this queue. And then we have a PyObject pointer, which holds the elements. And we are going to represent our elements with a PyList object, or just a normal Python list. So not a super efficient queue, but it will actually work. And then to define the type itself, we define a new PyType object. And we just need to start filling in all of the fields. So we start with PyVar object head init, and we give it the address of PyType type and 0. So this is kind of like standard boilerplate. You always start types with this, and that's because a PyType object unlike a PyMethodDef or a PyModuleDef, this is the actual type itself. So when you look up the address of the type object from Python, it will be the address of this object. So this sets up the type, which we're setting to be PyType type, because the types of types are type. And it sets our reference count to start at 0, which will get initialized to 1 when we ready the type in a bit. The next field, we've got the name of our class as the fully qualified name. So this is q.q. So this is saying this is the q class in the q module. And then there are 2 different kinds of sizes for types. So the first one is the TP basic size, which is the size of the instance structures that doesn't change. So for us, the size of an instance of our Q class is the size of this struct, which and this isn't always just the sum of the sizes of the members, because sometimes compilers will put padding between members because different types need to have different alignment. Your struct also might be specially aligned on different boundaries. So you always want to use the size of operator to compute this. You should never just put a value there manually. The next is the item size. And this is for things that are called variadic objects, which are objects where each instance might have a different size. The, I guess, canonical example of this is a PyTuple object. So tuples have a base size, which is a Py object base, and then an S size t, which says how many members there are. And then after that, there's a variable number of pointers, which are the actual members of the tuple. So tuples don't store a pointer to the members. The tuple actually contains the members directly. This allows us to access the members with 1 fewer dereference, and in exchange, we need to set this item size. I'd say that variadic objects are much less common in writing classes. Often you can just get away with storing a dynamic structure in a fixed size class, which is what we're doing here. So when you have no items, you set the item size to 0, which means you are not a variadic object. After that, you need to just start filling in all of the slots. And if you don't want to override a method, you leave it as null or 0. I have never written this by hand, nor do I expect anyone should or need to. I definitely recommend just taking a class that already exists, for example, this code here, and copy and pasting it and just changing the slots that you need to change. Because the order is seemingly arbitrary. Mostly it's when was this slot added. So you just kind of have to fill in the ones that you need. So assuming we've got a bunch of function implementations, we've got a dealloc function, which controls how we deallocate instances. So this is different from TP free, which is the function that frees the underlying memory. The dealloc function is responsible for decrefing all of the members that we have. So this is the final destructor for this class. And this function should delegate to the TP free to actually get rid of the instance itself. The types for all of these functions that I'm casting to come from even though they're not prefix, these do come from the CPython API. So destructor is the type of a dealloc function, for example. Our class is going to have a repr on it. Then we have our flags. So the flags that we have are PyTP flags default. Bitwise door with PyTP flags have GC because we contain a list which we need to traverse. So we've got a docstring. This docstring should also be defined with PyDocStirVar, just like docstrings for functions or modules. Then we have our traverse function and our clear function. We can implement a clear function because we can always shrink the queue back to empty, and that's still a valid queue object. It's just lost all of its references. Our queue is going to have an array of PyMethodDefs, which is going to be all of the methods on our queue that are not these built-ins. And then we have a new function. And this corresponds to the to the dunder new method, which should delegate to the TP-alloc to actually allocate the space for the instance, and then this initializes it as a Python object. Just a little side note, the new method is optional when you're defining a class in C. So sometimes you don't want to allow people to call your constructor from Python code, and you're going to have some helper function that's going to allocate your object and get it in the right state, but you never want someone to call this from Python. An example of this is built-in function or method, which is the type of the functions created with MethodDefs there's no way you can create a valid instance of this object from Python, so it doesn't have a TP new. And then when you try to call this class, there will be a Python type error that says, you cannot create new instances of this type. Yeah. So we have this struct, and there's a bunch of nulls in it, and we need to actually inherit the values for those. So I said before, like, you don't set the PyTP flags long subclass flag, it gets done for you. Or if you don't want to override a method, you just leave it as null. And the way you actually do this is you call this function type ready, and you give it the address of the type object. And what it does is it looks at the base class and goes and resolves all the methods statically and copies the pointers down to the corresponding fields. So this is how you finalize a class, and it's ready to be used from Python code. So one of the slots I went over and skipped was TP base, and this is the base class of your object. So this is like, I want to create a subclass of long, I would pass the address of pylong type. Or if I wanted to create a subclass of stir, I would pass the address of PyUnicode type here. And this is what is used when you call PyType ready to know who am I inheriting from. And if you leave that as the default, just like in Python 3, if you don't explicitly set a base class, it will be object, and you'll inherit everything from object. Actually, that's not always true. So for example, we are an instance of a PyType type. So it uses both the subclass and the type to know where to get its methods from, because this is like your meta class. And so the meta class here will define some methods for us also. And PyType ready can fail. So for example, if I set my TP base to a class which does not have the TP base class flag set, then I cannot create subclasses of that. And it's the PyType ready function that will do that check for us and fail and say, this is not a valid base class. So when you want to ready a type, you need to call the PyType ready, and you should do that from within the pymod init func. So you need to do it when you're setting up your module, but before you return the value. Yeah, so in the directory exercises/q, there's a q.c file, and in there we have the struct that I just walked through. And as an exercise, let's try to implement a push and a pop method that use the PyList object API, which is in the appendix. Oh, also, when you go to test this, you'll notice that the module is called Q and the class is called Q. Those are also built-in modules. That's a standard library module. I just forgot that when I wrote this example. So by building it, you're going to be shadowing the standard library. So you'll be like replacing the built-in library module, just like if you had written a q.py file. So sorry about that. question? This runs till 40. Is that 40 on the next hour, right?
Yeah, 440.
Okay, just making sure. Cool, thank you. Does anyone have any questions or need any help? There are no individual answer keys for the Q exercises. There's a single Q complete, which has all of them, but the push and pop are there if you need to compare there. self exists, when I call a method on self, it's going to exist for the whole lifetime of the function. So it's it's a borrowed reference. So you don't need to include direct reference unless you were going to put self in a container for some reason or whatever. Yeah.
Max size here, the current length of the queue?
Max. So this is a bounded queue. So as an argument to the constructor that's provided, you can pass the max size. It defaults to unbounded, or if you pass a negative number, it's unbounded. So when writing your push, you should check the length of the current elements list against the max size.
How do you define the current length of the queue?
So yep. So we've got one of the members is queue elements, and that's a PyObject pointer and semantic. And we know that this is a
Oh, right here.
yep. So that's a list.
Oh, and I can get the length of the list.
Yep.
Okay.
Yeah, which is one of the API functions in there.
And instead, yeah, I didn't know if there was an index, then I can assign it.
Actually, there's you don't even need to do that. So there's a couple of the append method is one of them in here. I think it's documented. Should be at least. Okay, cool.
Oh, yeah, right here.
Yep. Insert takes a sequence as the argument. So if that insert is more like actually sorry, insert takes the index, yeah. So you could insert it. Oh, okay, yeah. If you want to put it at the front, you could do that. Yeah. I would suggest putting it at the back because well, so if you insert into a list, it's gonna like shift all the elements, and then when you delete, it's gonna shift them back. Okay, cool.
So if push, what does push return if it needs to return nothing?
Oh.
It doesn't like me returning null, which I don't prefer.
Yes, I will mention that to everyone because that is a great thing to mention. Okay, so a question that was just asked is, what should push return because it doesn't have a semantic value that it needs to return? So just like in Python, all functions need to have at least some return value. There's no void type, and since we're writing a function for Python, when you write a function in Python and it has no return, it just returns none. So in our function, we also want to return none. So there's a global sentinel value called pi_none, and this is the value of none. There's also a macro called pi_ and then all caps return underscore all caps none. And what this macro does is it just simply calls pi_incref of pi none and then return pi none. And that's to remember that you need to increment the ref count of none when you return it because it's still an object and it still has a reference counting going on. Thank you for that question. Do you have a question?
So, in character settings, you need that to increase the reference count on element, right? That's what I'm seeing in the documentation, but you
Yes.
assign it here.
Yep, so assigning a reference doesn't increment the reference count. So the reference count is like how many Python objects own this thing. So when you call a PyList getItem, the macro reference count. It's just letting you look at the object that the list owns, but you haven't taken ownership yourself yet. When you want to take ownership, you need to explicitly call PyIncref. Does that make sense? Cool.
What are the difference between PyList size and PyList get size?
So PyList getSize is a macro, and it doesn't do any type checking. So when you call PyList size, the function, if you give it an argument that is not a list object, it will return an exception saying you must call PyList size on a list. If you use the PyList getSize, it's just going to cast it to a PyList object and like dereference it and just work from there.
Does that make better convenience with PyList size?
In this case, we know that we're the only one who can control what queue elements is, and we've set it explicitly to a list, so we can use the macro. I will say that it wouldn't hurt correctness to use the non-macro version. It's just slightly slower because it's going to do the type check, but it will always be true, so we'll always like branch predict true. Does anyone have a working implementation of push or pop or both? Great.
So when you take the element off the end list,
Yep.
and you've got to then slice to change the list size?
Set slice. Yep.
Set slice? No, set slice. Okay.
Yep.
But then do we have to do anything funny with the reference count?
So no, so the API function, so the references are owned by the list object, so the set slice function will correctly handle like decrefing the things that are no longer there.
Okay, but since I took the thing off the end before calling set slice, do I have to incref on
Yeah,
that?
so you need to now take ownership.
I see. Okay.
And I call this one, if I hadn't taken the item off first, would it then have decrafted? Does it?
Yes, so PyList let slice will manage the references of the objects that are deleted, or potentially no objects get deleted depending on what the bounds of the slice are. Yep. So when you take the object off the list, you need to first like incref it yourself to say like.
So this is actually wrong.
Oh, sorry. So yeah, so you're calling.
I'm taking it off and then I'm.
Yeah. So
slicing it.
this method or this function
Yeah.
returns a borrowed reference.
Yeah.
So it's letting you look at the element in the list, but it's still owned by the list. So then when you set slice and shrink it, you're now going to be working with a potentially invalid object. So you need to first, before you delete it, say, now I want to own it.
Before I do the set size or what? Do I need
Yes,
to- yeah.
because once you do the set slice, it's going to call decref. Yep.
Yeah.
So that's actually kind of a subtle bug you could write, because if the list is not the only owner, then it might still be valid. But if the list is the only owner, when you call the set slice, it will deallocate the object, and now you're just calling like incref on some random memory. Yep.
Push. So
Yep.
it's just PyList depend the queue.
Elements and then end. Yep.
Yeah. So I just change the signature from like taking R's or anything like that to just.
Yeah. said. Oh, I said use that, but I don't know what's the other argument for that. I don't think this also works.
Yeah.
So
Yeah, I mean, I just tested it. So like an import AQ object,
Yep.
push something, and it shows. I mean, I didn't iterate through it, but
Yeah. Yep. Great. Does anyone else need any help? Yeah. So it's a lot of the CAPI functions in general are like the most general type of operation that could be performed. So, for example, like you don't have set slice or like set item, or there's basically like set slice and get slice are designed to do all the functionality that you could build on top of, and then those are methods.
So it doesn't say whether the indices are inclusive or exclusive.
Inclusive, exclusive. They're slice style, so it's inclusive on the first, exclusive on the stop. Also, you might have noticed from the appendix, set slice takes null, meaning delete. This is a kind of pattern in the CAPI in general. For example, there's getAttr and setAttr, but there's no delattr. The way delattr works is null is passed to setAttr. So, or there's no, there's getItem, but there's no, and setItem, but there's no delItem. Same idea. You pass null to setItem. There are helper functions that will do this. There's like PyObject delItem or delattr, but it's just an alias for PyObject setAttr of null. What? Nice. And respects the max size. Great.
I was just going through your solution here, and if you actually call the append and it works,
Mm-hmm.
then it worked, and then you return null. So what is returning null compared to returning none?
Oh, sorry. That you're reading the branch inverted. So PyList append returns true if it fails.
Oh, I just looked it up.
Oh,
It says return 0 if successful.
oh, sorry. You're right. Yes, you are correct. Sorry. So the branch is. Yeah, I was just saying that wrong. So if it's 0 is false. So that's
0 is false.
yes.
Okay.
And then 1 is true.
Okay, so,
so-
if it doesn't work, it returns null.
Yeah.
If it did work,
Yes.
it would do. Wait.
Sorry.
Okay, so then it would just come here and return none.
Yep.
Okay.
So null is the sentinel that says an
Because
error.
in Python, when you call append, you don't really set it equal to anything, right? You don't
Yeah.
say a equals.
So this is because append needs to signal whether it worked or not, right? So append can fail because it could fail to allocate or something, right?
Okay.
So if PyList append fails, and it almost certainly won't, but it could because
Out of memory.
exactly, then it needs to signal that success or failure flag. So it does that with that Boolean, and so if it
With
fails,
this one?
the return type of PyList append.
Oh, yeah, yeah.
So then if PyList append failed, an exception will be raised, which means, and so like 0 or 1 in this case is the sentinel value, or -1 or whatever it is.
Okay.
And then we need to propagate that failure.
So my question is, why do you even have it? Why don't you have void here?
Because all Python functions need to have some return type.
Oh.
And that's just like, for example, there's no void functions in Python. Functions just return none if they have no return, right? Like list.append returns none.
Okay.
But PyList append is the CAPI equivalent, so it doesn't return none. It just
So this is a
macro.
pointer to PyObject as well.
PyNone is a PyObject pointer. Yeah, so like PyList append really can be thought of as void, which could raise an exception.
Okay, so
If that makes
you're
sense.
returning null, that would actually like throw an exception, whereas this none is a valid
Yes.
return.
Does that make sense?
Okay.
Cool. Oops.
What did you put in it?
Sys get ref count.
Yep. Sorry. What objects are in the queue? Integers.
X is one I popped from.
Yeah.
it's an
Okay.
integer.
So I'll mention this forever.
The low number of
Yeah. So someone just checked the ref counts of the objects that they popped from the queue, and they wanted to know why they were really high. So if you push into the queue integers that are small meaning less than 257, or really not negative numbers, meaning greater than or equal to -5. So integers in the range inclusive -5 to 256 are interned in Python. So there's a single static array. When you want to create a new integer object, it indexes into that array and it grabs it if it's small. So the integer 1 is like object identity is 1 is always true. That's an implementation detail of Python. So that means if you look at the ref count of small integers, they should be very large because other people might have a reference to 1 or 2 or something elsewhere in the interpreter. So if you want to test the reference count, what you could do is instead create your own object, say like x equals just object, open close paren, to create an instance. Then you would maybe have more intuition for that, because in that case, there should be exactly one reference. If you're using IPython, which I have in the virtual env, know that if you ever repr the object, if you just write like x, that's going to save it in a lot of different places, and the reference count's going to be very hard to understand because IPython has like underscore is the last evaluated thing, and underscore is the second to last evaluated thing. So it's going to get saved in all these different places. PyList set slice would fail if you're setting it with not deleting, but if you're actually setting and you give something that's not iterable.
Right, but I mean, like in your sample code, you actually check the error return.
Could it fail? I don't know the implementation details of set slice. One thing that it might do, which could cause it to fail, is let's say I've got a very long list and I want to shrink it. It might reallocate the buffer instead of having a massively overallocated buffer with a huge capacity. It might say, well, you probably don't need that large capacity. I'm going to just move you to a smaller buffer. That reallocation could fail. So there's no documented thing that says you don't need to check the return of that. So I would say you have to check the return. There are some functions that return values that you don't need to check for failure. Those are like very explicitly called out. Like this can't fail. Like there are like PyTuple new of an empty tuple. The docs were just changed to say that empty tuple never can fail. It's always going to give you a valid thing. Actually, I don't know if those went through. There's an open PR at least, or potentially merged. Does anyone else have working code of at least push or? Okay, I think we're going to do this for maybe at most like 3 more minutes and then move on. And then I'll be around all week if people have questions about this, if you want to continue the exercises on your own. Yep.
When I push, do I need to ink that one as well, or is it
So,
already done it because it's in the clocks?
PyList append will increment the reference count because the list API says I'm going to, I'm now taking ownership of that, so it's going to do that internally.
Okay. But I just have a segmentation for when I try to pop a value.
When you tried to pop?
Yeah.
So
something's wrong.
you, all right, so let's look at your push
Oh wait,
there.
I didn't recompile.
Oh, okay, yeah. Yeah, as another reminder, gotta remember to recompile the C. It's, as a Python developer, often you're like edit and run in the REPL, edit and run the REPL, but there's the extra step of recompile. that is the next section. But if you look at the thing in the docs, the next very next section is debugging with GDB. So we'll get there in just a minute. Okay. Actually, it's not the next. It's after the next section. We'll get there. That's the, all right. So in the interest of getting through all the material, I'm going to move on. If you want to finish the exercises later or have questions, I'll be around. So we all just wrote some code and spent some time on that. We've written a little bit of code today. And you probably ran into like a bunch of issues in the REPL already, and what are these? So to echo the warning again, writing C extensions is hard. So just like make sure that it's not already written. Make sure you're not writing code that doesn't need to be written in the first place. So C is statically compiled, and the compiler is going to catch a bunch of failures that normally the interpreter would. So you don't have to worry about name errors or undefined variables or things like that. If the code compiles, it's like at least those things are fine. But when writing a C extension, the most common issue you're going to run into is a problem with reference counts. Like I'm sure everyone's already been like, oh, do I need to incref here? Do I need to decref here? This is like, that question never goes away. So you always need to think about these kinds of things. So there's two different flavors of reference count problem. There's a reference surplus, which means that incref was called more times than needed to be. And this is a memory leak. This means that all of the pairing, there's not enough pairing PyDecref calls because incref was accidentally called. So the object never hits a reference count of 0, which means it never goes away. So the most common place you will see this, or the easiest place to look for this kind of leak, is to go find function calls which return new references. Sometimes you might think, oh, this returns, you might forget that something returns a new reference and you need to call decref on that when you're done. There are other cases where you don't explicitly call decref, but you give ownership away. For example, you might have noticed that PyList setItem, the docs say that it steals a reference to its argument, which means that you give it a reference that you own, and you no longer own it after calling that function. And that's to, those types of functions exist as optimizations. For example, a very common pattern is create a new object and immediately put it in a list, so you don't have to then also call decref. So those are places to look for new references. There are a little bit, so reference leaks like this are hard to detect when you run your unit tests because often the code will run. Like the code produces the correct values, it's just the objects never get deallocated. So unless you have a very large or long unit test, you might not leak fast enough for it to be noticeable. So a little smoke test that I sometimes run, it's not comprehensive in any way. It's just if you think your function should be reference neutral, meaning at the end of the function there shouldn't be any more or less references than when I started. If you just call that function in an infinite loop in the REPL and watch your memory usage, if it goes up, then it means you're leaking where you didn't expect. It might not be totally flat because there are cases where Python overallocates internally, but eventually it should flatten out. Like if you're creating some integers, it might pre-allocate the buffer of integer objects, and then eventually it should be flat. Though the inverse of this is not true. So if memory usage is flat, it doesn't mean that there are no leaks. So if it grows unbounded, you're definitely leaking. But if it's flat, you might still be leaking just objects that you don't know should have been freed yet. For example, if you were leaking references to small integers, they're already allocated and they're still being used by people, so you still might be leaking those. Another common thing that happens is you could accidentally leak a reference to self. So you don't actually have to decref self at the end of your function, but if you accidentally increft self in a method, that means that that object will never go away. Even though if you call that function in a loop, you're just growing that counter, and self will never get deallocated when it needs to be. Yeah, so all the global sentinels need to be reference counted just like everything else, and that's mainly just to maintain the consistency of the interpreter. Although I would say if your code has
reference surplus on something like PyNone, that has no practical problems, or at least in current Python, though they say you do need to incref and decref them, so that's not a guarantee that it will never cause problems in the future for future versions of Python. Then the more explosive failures are in reference deficits. So this is when you call decref on an object that you don't own, or you call decref too many times. And this is bad because it means that at some point in time, someone will have a reference to this object that they believe they own, and it will have been deallocated because someone's going to call decref, and then it will deallocate it, and someone else has a reference to that. And now this leads to a use after free bug. So these are common security problems. They also are very hard to detect because the failure will be very far away from the actual bug. It's going to be the second decref. So it's not where the first decref was. It's going to be the last one, the person who's calling decref on the invalid object that fails. It also might not fail at all because it might just decref whatever object got put there afterwards. So these bugs are much harder to detect. So the most common place to look for bugs like this are call sites that return borrow references. Make sure people aren't treating them like owned references. There's no difference at the type level in C between a borrowed reference and an owned reference. They're both PyObject pointers. It's just how you use them. So you need to read the docs carefully to know which is which. In the CPython official docs, any function that returns a PyObject pointer is assumed to be a new reference. It will explicitly call out if it returns a borrowed reference. In my appendix, I've explicitly, I believe, said whether every function returns a new or a borrowed reference. I don't have a quick smoke test like I have for reference leaks for deficits. Call your function in the REPL. If it segfaults, there's a bug. Might not be a reference deficit, though. So now that I've scared you with the problems, I'll talk about how to fix them a little bit. So GDB is the GNU debugger. It's a debugger for C and C++, I think Fortran, other compiled languages, anything the GCC suite knows about. So if you're used to running Python under a debugger, you know about PDB or PDB++ or IPDB or one of the other flavors. They're all built on top of the same core, which is BDB, which is the Python Standard Libraries debugger. And this debugger is great for Python. It has a lot of features that know about Python, but unfortunately, it can't step into a C function. So if you've ever been the debugger for Python and you call list.append and you hit step, it just goes right over it because it doesn't know how to actually go line by line through C code. On the other hand, GDB knows all about the C code, but it doesn't know anything about the Python, so you can't step through the Python. So you actually, when writing a C extension, need to kind of be in both debuggers depending on what kind of failures you're trying to look for. So I would say start with the GDB because you can still inspect the CPython stuff, or the Python side if you need to. So when you are trying to debug an extension, the first thing you need to do is build a debugged compatible version of the interpreter. So in the setup script, the reason I didn't have people just apt-get install or pacman install Python is that normally those don't have the debugging features. So the things that you're going to get from a debugging Python are debugging symbols. So in compiled programs like C or C++, there's a symbol table which has the names and some line information. So given any single instruction, it knows what the line information. If you don't have this when you step in with GDB, all your functions are going to be question marks because it doesn't know the name or the locations of anything. So you can often get those from your package manager, but the thing you can't get is that debug versions of Pythons have a bunch of assertions in them. So one of the assertions is that if you call pydecref and the reference count is less than 1, immediately abort. So this will catch some types of reference deficits. For example, if I pass an object with a reference count of 0, meaning it was just deallocated, abort and say, this reference count is wrong, this doesn't make any sense. And you'll get a stack trace in C, it'll do a core dump, and it will also print the Python stack trace so that you can have a better sense of where you are. Another thing that the debug version of Python does is it changes the definition of the PyObject structure itself. And it adds 2 private fields, obnext and obprev. And what this does is it actually turns every single Python object into a doubly linked list so that it can never lose a reference to an object so that it can find leaks differently. So you have a bit more debugging stuff. So there's a whole bunch of different debugging things that are enabled by this. I won't cover all of them, but just always run with the debugging enabled Python. If you want instructions on that, it's in the setup M script for different environments. So to actually to debug your extension, the way you do that is you run Python itself under the debugger. So you run gdb Python, and that's going to print the GPL stuff and then tell you a bunch of other options, and then it's going to drop you at a REPL. So to actually debug our extension, we're going to want to set a breakpoint, and the way you do that is with the b command or break command, and you give it the name of the file. You just need the base name of the file. You don't need the full path or anything, and then colon and the line you want to stop. You can also give it the name of a function or the name of a function in a particular file. And then you're going to get a warning that says that it doesn't know what this file is and that do you want to set a breakpoint there anyway. So this is because when you define an extension module, what you've really done is you've built a shared object or a dynamically loadable library. So when you call import, it's going to actually open that file and link against it and bring all of its symbols into the Python single program. So at this point, when you've just called gdb Python, we haven't imported your extension, so it doesn't know about it yet. But you can tell gdb, yes, that's what I really meant. I want to set a breakpoint on this file that doesn't exist because I know it will exist in the future. There's also conditional breakpoints, and this is a feature I don't see a lot of people using, but they're super helpful. So after you set a breakpoint, you can say break if, and then any arbitrary C expression. And that expression will be evaluated with the context on the line that you're setting that breakpoint. So for example, if you have a bug and there's a loop and it's called 1,000 times and you just want to stop on the last iteration of that loop, you could say break if n is equal to 1,000 or something. And GDB will check every time it gets to that breakpoint, do I need to stop here or not? And that can dramatically speed up debugging. This is also a feature of PDB. I see my coworkers not use this all the time. Makes me so frustrated. So try it out. So to actually run the program under the debugger, so we got our breakpoint set, and we're ready to stop. We need to run the code. So the run command in GDB forwards all of the arguments to the command line of the program that you're running. So for example, if we just want to run a single Python file that invokes the behavior that we want to test, you could just say run and then the Python file. But again, since this is just forwarding everything to the command line, you can also just say run and forward no args. And this is going to drop you in a Python REPL, which has everything, which is under the debugger. So you can manually, from the REPL, invoke the code that triggers your breakpoint. I do this all the time. The run command also does shell escaping. So sometimes the normal Python REPL is less ergonomic to use than IPython. So you can say run and then within back quotes, which IPython, and that will run IPython under your debugged Python, so you have access to your history and tab completion and all those things. And then you can just call the code that you want to call. For example, if you just want to debug one function when n is equal to 10, you can just call your function with n equal to 10. So once you're stopped at the breakpoint, GDB has a feature called TUI mode, which is the terminal user interface. And this is basically an ncurses application built into GDB. And if anyone here has used PDB++, it's kind of like sticky mode. So it ends up jumping you into a multi-window terminal session where the top window has the source code and the bottom window has the REPL, which you can interact with. But there's a bunch of different window types, and you can change how they're laid out, even all within a single terminal. So another window can hold the values of all your registers, which depending on what kind of code you're running is useful. One will show you the instructions, like the disassembly of the code that's being run. I think there's one that has all the variables that are in scope. So TUI mode is very powerful, and it is a nice way to not have to constantly be bouncing back and forth between your editor and the debugging session. So you're stopped at the breakpoint, and you actually want to understand the state of your program. The P command, or the print command, takes any C expression and it will evaluate it with all the variables in scope. If you're used to PDB, in PDB, you can just write code in the REPL and it will evaluate it if it's not any other command. But in GDB, that's not true. So you always have to put a P in front of all of your expressions. And when it's done, it will say $1 is equal to 4. And what this means is that the results of every expression that is saved in GDB, and you can fetch that result by using that value. So if you want to use the result of any command in a future expression, you can just look that back up with $1. And then there's no type function in C, so you can't inspect the type of an expression or of a variable as just a C expression. So there's another command called whatis, which tells you the C type of any expression. And you can use the saved values in whatis also. Basically the same rules as the print. You can also navigate through your program. So there's the S or step command. Next, until says execute until the line of code I'm on is greater than the current line. So what this is, the difference for this and next is that if you're in a loop, next, and you're at the bottom of a loop, next brings you back to the top of the loop and starts the next iteration. Until brings you to the next source line, so it'll bring you out of the loop, even if it will continue more iterations. And then finish, so if you're coming from PDB, the command is called return, or R. In GDB, that's called finish, and that says execute until the return, but stop on the return line so you can inspect what value you're returning with. And then there's up and down. Another thing that will get you if you're used to PDB, in PDB, up is aliased as u, and in GDB, until is aliased as u. So if you actually just wanted to walk up the stack and you type u, you'll execute the next line of code, which is often not what you want to do. So there's no alias for up, it's just up, it's already 2 characters. So these show you the frame above you, and then down shows you the frame below you, the C stack frame, not the Python stack frames. You can also set and remove breakpoints from a breakpoint. So setting a breakpoint is the same as before. Clearing a breakpoint is just clear and then whatever identifier you use to set the breakpoint. So I mentioned in the instructions that we needed to use GDB and not LLDB, and that's not just a preference, that's because there's some specific stuff for GDB. So GDB has an extension system. You can actually write extensions for GDB in Python. So Python can be, or GDB can be built with a Python interpreter in it, and you can write new commands and new pretty printers. And CPython, the repo, or the project, has an extension for GDB, which is written in Python, which is pretty printers and commands for debugging Python extensions, which is very circular, but also really cool. So by default in GDB or in LLDB, if you evaluate a PyObject pointer, it's just going to say PyObject pointer and the address. And that's kind of all you get. If you wanted to know the type, you would say, give me the object, get its type, get the TP name. If you want to know the value, good luck. You need to understand the internal structure of whatever type you're working with. However, there's a GDB extension, which is installed as part of the setup env. So if you want to see how, basically all that consists of is putting a Python file with a particular name in a particular place. That's done in the setup env. You can see how it's done there. Once you've gotten that extension running, you also need to change something about your include path for GDB, which is, I don't know if I put that anywhere. So we can do that together. But so now if you have a PyObject pointer in the REPL, it will evaluate to the name of the type and the address. So it's a little nicer. It's closer to the repr. This is for extension types, or any type that's not a primitive. But a bunch of the Python primitive types will just actually show you their repr. So for example, if I look at the Q elements, it reprs as an empty list because it's a Python list. And if I look at what is, it's still a PyObject pointer. So if that list was populated with integers, it would show me a list with 1, 2, 3 instead of just PyObject pointer. So this makes debugging much, much faster because you can just quickly understand like what are the values that I'm working with. And then the extension also provides a couple specific commands. So one is pybt, which says print the Python stack trace that led us to the current C code that we're in. And a note, this order is reversed. So normal Python stack traces are most recent call last. This is most recent call first. And that's because that's the stack trace format that GDB itself uses, so it's a little more consistent. PyList prints the source code of the stack frame that you're in, the Python stack frame that you're in. So if I'm in a C function call, that's being invoked by some Python, and we'll print that source code around that. PyLocals prints all the variables that are in scope in the currently selected Python frame. PyUp and PyDown move the currently selected frame up or down. So PyLocal, the currently selected Python frame starts as the bottommost frame. But if I call PyUp and then call PyLocals, it will show me the variables in scope in the Python function which called the Python function which called my C code, and so on. PyPrint just takes the name of a variable in scope in the currently selected Python frame and prints it. Yeah, I think I'm like out of time now. So, right? So there's an exercise here, which is just to teach people how to use GDB, but unfortunately we don't have enough time to get to that. And there's another section that's pretty brief. It's just teaches you how to add attributes to your class. So we've talked about how to add methods, but sometimes you just want to expose a single attribute, and there's 2 different ways to do that, which you can go over on your own if you are interested. Thank you very much.